Right. So just like I was saying, so now let's talk about how to represent le vecteur vitesse et le vecteur accélération in Cartesian coordinate system and the cylindrical coordinate system. That's what we want to do. And then next time we'll look at le mouvement relatif. We'll be talking about things like la vitesse d'entraînement, la vitesse de Coriolis, and all that good stuff. But for now, let's first of all talk about, la vitesse et l'accélération en coordonnées. That is Cartesian coordinate system and the cylindrical coordinate system. Right. So Tassila is not here, but anyway, we'll just continue. I don't know what might be, holding her back. Right. So let's talk about the representation of le vecteur vitesse et le vecteur accélération in the Cartesian coordinate system. Again, if you notice anything, if the screen disappears and all that, just let me know. Otherwise, I'm going to continue with our lesson. Just going to create a new page like so. Boom. Right. So, bien. We know that now I'm talking about the Cartesian coordinate system. So here I'm just going to say Cartesian coordinate system. Cartesian coordinate system. So we know that le vecteur position, the expression for the vector position, c'est simple. Elle est simple, l'expression. So we have OM is going to be equal to, we know that it is x, EX, plus y, EY, and then plus z, EZ. And then let's say our referentiel is going to be R with origin O, and then we have X, Y, and Z, like so. So this is our OM. So X, EX, Y, EY, and Z, EZ, and then we have this reference frame. So by definition, what is velocity? And then on sec, let me just remind you, on sec, we know that the derivative with respect to the derivative of EX, let me just say the derivative of EX with respect to time in the reference frame R is equal to the derivative of EY with respect to time in the reference frame R is equal to the derivative of EZ with respect to time in the reference frame R. They are fixed, so the derivative is going to be equal to 0. And then by definition, so par définition, we know that the velocity of a point M in our reference frame R is going to be the derivative of the vector position par rapport au temps. So this is what we have. So this is how we can write it. So the velocity, this is by definition. By definition, the velocity of a point M in our reference frame R is going to be equal to the derivative par rapport au temps of the vector position. So what is our vector position in this case? Well, our vector position in this case is d dt, and then OM, we know that OM is equal to what? Is equal to EX plus Y, EY, and then plus Z, EZ, like so. And then we know that the differentiation operator is distributive. If we have the sum, we can distribute the derivative part, or the differentiation. So this is going to give us d dt, and then EX, and then même chose, d dt, and then Y, EY, and then plus d dt, and then Z, EZ. So remember, X is a function scalaire, and then EX is a function vectorielle. Same. Y is a function scalaire, EY is a function vectorielle. Même chose, Z is a function scalaire, EZ is a function vectorielle. And so we have a product of two functions here. So when we're taking the derivative, we have to differentiate one first, and then leave the other one, and then differentiate the other one later on, and then leave the first one. So what I'm saying here is when you have a product of functions, we have d, we have d dt, we have d dt, and then we have x, like so. Okay, so x, and then we leave the EX. So I'm just going to maybe put this in parentheses, like so. Now let me just maybe do this, and then EX, like so, and then plus, now we leave the x, then we differentiate our ex, like so. Même chose for y, so d dt, like so, and then y, and then y, and then now, and then d dt, like so, and then I'll put the y in front, like so, and then I'll say ey, like so, and then you can continue, do the same thing for z. Now, this is 0, and this is 0. Same thing for the part where we'll be differentiating ez, it will also get 0. So we have 0, 0, 0, 0. Now, finally, the derivative of x with respect to time is going to be x point, and then ex. So this is a dérivée temporelle. It's known as a dérivée temporelle. We are differentiating with respect to time, so we put a point on top to mean that we're taking the derivative of x with respect to time. Dérivée temporelle. In the Cartesian coordinate system, we can have what is known as a parametric representation of any point in space. Maybe x. I'll show you an example. I'll show you an example later on. But to just cut the long story short here, when we're differentiating with respect to t or with respect to time, we have what is known as a dérivation temporelle. And then to indicate that we are differentiating with respect to time, we put a point on top, ex, and then plus y point, ey, and then z point, ez. So this is the vector vitesse in the Cartesian coordinate system. So this is how we write the vector of vitesse in the Cartesian coordinate system. Is it okay? Je passe?
You can just repeat a bit.
Okay. So what I'm saying here is this. We know we have the vector of position, which is the position of any point in space in the Cartesian coordinate system is given by ex, y, z, ez. Like I said, like we wrote on the previous page. So this is the vector position. Now we know that in the Cartesian coordinate system, the unit vectors are fixed, meaning par rapport au temps, that is. So if we differentiate with respect to time, the vector ex will get 0 because it's fixed. It does not change with respect to time. Okay? So it does not change with respect to time. Same thing for ey, same thing for ez. Is that a question? Let me maybe move to the browser and see what is happening. Okay. So you're saying I restart? Okay. Yeah. So what we said here is, in the Cartesian coordinate system, any point in space is given by this expression or this equation that we've written here. So if we have a point M in space, then its location is going to be given by this equation that we have here. So this is known as le vector position. So we have OM is equal to x, ex, and then plus y, ey, and then plus z, ez. So this is what we have. This is le vector position. Okay? And then here I'm saying on sec, we know that just like we wrote on the previous page, that the derivative of ex with respect to time is equal to the derivative of ey with respect to time is equal to the derivative of ez with respect to time is equal to 0, because the vector unitaire, the vector directeur, which is ex, ey, and ez, they are going to be what? They are going to be fixed in the Cartesian coordinate system. And so when we differentiate with respect to time, these vectors will get 0. Now we want to apply what is here to what we're going to do here. So by definition, we know that velocity, to find velocity, you have to differentiate le vector position par rapport au temps. Okay? So that's by definition, that's what velocity is. The rate of change of or the rate of change of whatever, the rate of change of position with respect to time. That's by definition, that's what velocity is. Okay. Now, what we want to do here is, since we have the expression for OM, we substitute this OM that we have here with this expression we have here. X, X, Y, Y, and then Z, Z. So up to this point are we able to follow the transition from what we have on top to what we have now? Is it okay? Yes. Who is that?
Yes, I'm following.
Okay. Now that we have this, remember that X is a function scalaire. Is a function scalaire. X is a vector. We can see that X is a vector. I'm sure this is Tassila. She's going to say that I repeat. So, bien. So, this, we have a product of functions. If you remember from, your lessons, your mathematics lessons from, grade 12, when we have a product of functions, how do we differentiate? We apply the product rule, right? We apply the product rule. So here, to be precise, x is a function scalaire. X is a vector. Same, y is a function scalaire. Y is a vector. Z is a function scalaire. Z is a vector. But it's a product of two functions. It's a product of two functions. Fonction scalaire, fonction vectorielle. Même chose, y, fonction scalaire, fonction vectorielle. Fonction scalaire, fonction vectorielle, z, z. Okay? So we apply the product rule. So it will be the derivative with respect to time of x, and then we leave x untouched, and then plus x, and then multiplied by the derivative of x with respect to time. And then we do the same thing we apply the product rule for y and y. We apply the product rule for z and z. Yeah? We will have what we have here. Okay? Or we know that the derivative of this quantity that we have here, of this quantity that we have here is equal to what? 0. Because the vector is constant. This is why here I reminded you that on sec, the derivative of x with respect to time is going to be equal to 0. So this is why we have 0 here. And then this is why we have 0 here for y. We also have 0 for the derivative of ez with respect to time, because these vectors are fixed in the Cartesian coordinate system. C'est bien. Okay. Now that when we eliminate these vectors, let's now look at this quantity here. So let's look at this quantity here. So the derivative of x with respect to time, it is a dérivé temporel. It depends on time. Now, to show that we're taking the derivative with respect to time, what we're going to do is that we'll put a point on x. So x point. So we'll have a similar quantity, but for y. So we'll have the derivative of y with respect to time. If you expand everything, you will have the same thing for y. So it will be also a dérivé temporel for y. So we'll put a point on top of y to show that we are taking the dérivé temporel. La même chose for z. We have a similar item. So it will be the derivative of z with respect to time. So it's a dérivé temporel. So we'll put a point on top so that we'll have z and then ez. C'est bon? So this is the expression of le vector vitesse in the Cartesian coordinate system. So this is what we have. C'est bon? Je passe?
A bit lost here when you did the derivative of x. And the last part here.
This part.
Start from d over d x to x plus x. How come here did x 2 times?
We've applied the product rule. Now let me just quickly reconnect here. I can see that
Can you get me?
Yes, I'm able to get you. I've just reconnected. Tassila wants to join.
Yes. Here. Then I'm lost from here where you've done x 2 times y dt derivative of x over times x 2x plus x derivative of 2 times
Well, we've applied we've applied the product rule. Do you remember the product rule? Yeah, we've applied the product rule. So we differentiate the first item, which is x, and then we leave the second one alone. Okay, we leave the second one alone. That's why I'm saying d dt x, and then I've just left the x alone. And then the second part, we leave the first one alone, which is x. So we've left x untouched here. And then we differentiate x. You understand? Same thing for y. We differentiate the y and then leave y untouched. So we have d dt y, and then y, we leave it untouched. Okay? And then we'll leave y untouched because we are from differentiating it. And then we'll differentiate y. Same thing for z. So that's why it looks like we are doing the differentiation twice on the same on the same item, which is x or y or z. It's because we are applying the product rule. You understand?
Yes.
Right. So, and then d with the derivative of x with respect to time is a dérivé temporel, and so we put a point on top here on top of x to show that we are differentiating with respect to time. La même chose pour y, la même chose pour z. Then the derivatives of the unit vectors ex, ey, and ez will be equal to 0, just like I've indicated on top here, because in the Cartesian coordinate system, these vectors are going to be fixed. C'est bon? Je passe? So let's now talk about le vecteur accélération. Le vecteur accélération, c'est la même chose. Même chose. But here we take the second order derivative. Now let's remember that by definition, acceleration is the rate of change of velocity. So by definition, the acceleration of a point M in the reference frame R is going to be equal to the derivative of the velocity of the point M in the reference frame R, and then divided by time, like so. You understand? And so we know that the expression for velocity, we are from finding it here. We have it here. So this is going to be equal to, and then dt, and then the expression for the velocity, we have it. It is x point ex, and then plus y point, and then ey, and then plus z point ez, like so. So this is what we have. I've just copied the final answer here and put it here. Then here we do the same thing. Okay, we do the same thing. X point is a function, x is a vector again, so we have we will do the product rule here. Let me just write everything. So let me just write everything, but then I'll allow myself to sort of like have a little bit more room. So I'll move to the left, like so. And then it will be dt of x point, like so. And then we'll leave x alone. Maybe I'll even do this, like so. Are you able to follow? Wiza, Natasha? C'est bon? So, and then plus, and then I'll put the x point here, and then here I'll say dt, and then x, then I'll continue. I have the same, I have dt of y point, and then here I'm going to have y. Now let me just reconnect. Right. So I just got disconnected, but then are we able to follow? Are we following?
Yes, I'm following.
Okay, that's good. So, right. So, and then plus, okay? And then we leave y point alone. And then we differentiate with respect to time y. And then we do the same thing for z. So we differentiate z point. We differentiate z point. Like so. So here you have dt and then z point. And then we leave z alone. And then plus, we now leave z point alone. And then dt of az. Or this part here is 0. This part is 0. And then this part is 0. Then finally, what we'll have is here, remember we are differentiating again, but differentiating x point. So it's a derivative temporal. So we have 2 points. So x point, like so. And then ex plus y point plus ey. And then plus z point ez. Je passe? C'est bon? Is it clear? Okay. Oui, ça. Très bien. Natasha. Tasila. Yes, what is your question? Oh, okay. Right. So we've represented le vector accélération in the Cartesian coordinate system. We've also represented le vector vitesse in the Cartesian coordinate system. We also have le vector position in the Cartesian coordinate system. Let's now move to the cylindrical coordinate system. We'll do the same thing. Le vector accélération, le vector vitesse first, and then le vector accélération, and then we'll call it a day. The next time we'll look at le mouvement relatif, where we talk about le vitesse d'entraînement, le vitesse de Coriolis, and all that good stuff. So let's go to the representation of these vector quantities v and a in the cylindrical coordinate system. Let me just allow myself to create a new page here, like so that we have organized notes. So like so. Now right. So maybe let me also connect on my phone so that I'm able to notice when I get disconnected. So what I want to do is I'll connect with my phone. I'll just give me 1 second. Let me just look for the link and connect with my phone so that I know when I'm disconnected.
Wait, I have a question as well.
Okay.
Just inquiry. So if we hear something like autonomous direct,
Autonomie directe.
it has to do with autonomous direct. It has to do with the Cartesian.
No, it is a system. Autonomie directe is what the unit vectors ex, ey, and ez are going to form. They're going to be autonomie directe. Meaning, if you take the vector product of any of the two quantities, will give us the other one. In the positive sense, that is. Okay? But then we'll add the negative if we go in the opposite sense. Okay? So autonomie directe is what the unit vectors form. Ex, ey, ez, euro, phi, ez.
Okay.
Right. So let me just get rid of the sound here. Right. Bien. So let me now talk about the cylindrical coordinate system. Now that everything is okay. Sorry. Okay. Where am I? Here. Bien. Well, what did I just do? Okay, I'm back. So, for the cylindrical coordinate system, c'est la même chose. We'll first of all write le vector position. And then after, now I can see that my screen has disappeared. Is it the case for everyone? Has the screen disappeared?
No.
It's still there? Okay, I think it's my network. Fine. So just like for the Cartesian coordinate system, we will have to write le vector position. Le vector position in the let me just remind you, it is going to be rho, euro, and then plus z, and then ez, like so. And then we know that by definition, the vector of vitesse of a point M in the reference frame R is going to be the derivative of OM par rapport au temps. OM is this expression that we have on top. Donc, directement, we write, so we have d dt of rho euro, and then plus z oz. Okay? And then here we have a product. Rho euro is a product. We apply the product rule. So we first of all differentiate rho. When we differentiate rho, we will get rho point. And then we leave euro alone. So we'll have euro. Like so, we leave it untouched. And then plus, we now leave rho untouched. So we put it. And then we now differentiate euro. Remember, here, we have to be very, very careful here. We have to be very, very careful. Normalement, we know that euro is equal to what? It is equal to cosine theta ex plus sine theta ey. C'est bon? Now, normally, this euro is written en fonction de theta. En fonction de theta. But here, I want to differentiate it with respect to time. Time is not part, it's not part of the variables here. Time is not part of the variables. So, what we do is, since I want to differentiate euro with respect to time, I'm going to say, let me just write it in a different color. So what we're going to do is, we know, if I want to differentiate euro with respect to time, what I know is this. Let me put it in a box. What I know is this. What I know is that the derivative of euro with respect to phi is equal to e phi, like so. And then the derivative of e phi par rapport à phi is going to be minus euro. This is what I know. I don't know what this derivative, normalement, I don't know what this derivative is. So, what we are going to do is, we are going to write this in the following way. So, this is going to be equal to the derivative of euro, and then we divide by, so the derivative of euro, and then we divide by phi, and then the derivative of phi with respect to time. Now, you can see that this and this can simplify. So we will get back what we have here, the derivative of euro with respect to time. So this is what you should always do. When you are differentiating with respect to a variable that a function does not depend on, you do something like this. Here, the variable that we want to differentiate with respect to is t. But euro does not depend on t. It depends on phi. Normalement, we don't know how to calculate. directly the euro par rapport au temps. So what I know is I'll use what I know. So which means I'll pass by, this phi. I'll use this phi as my intermediate, form of differentiation. Okay. So I'll say the derivative of euro with respect to phi, and then multiplied by, I'll repeat this. This is what is here. So you see that we have this representation here. So this representation on the right is equal to whatever we have on the left. Or the derivative of euro with respect to phi is a phi, like so. And then the derivative of phi with respect to time is going to be phi point. It's going to be a dérivé temporel. Okay? So that's why we're going to say phi point e phi. So this is our result here. I'll put it here. Phi point o e phi. Like so. Okay? So this is what we're going to have. Now let's differentiate z. So for z, what we're going to have here is going to be plus, like so, plus, and then we differentiate z, so that is going to give us z point, like so, and then we leave ez alone, and then we come and differentiate now ez. We leave z alone, but the ez in the cylindrical coordinate system is the same as the ez in the Cartesian coordinate system, so it's constant. And so the derivative is going to give me what? 0. Okay? But I'll just write it to show you what's happening here. Okay, and then I'll show you that it's now 0. And then z, and then the derivative of ez par rapport au temps, well, this quantity is going to be equal to 0. Finally, our answer is going to be rho point euro plus rho phi point e phi, like so. So for example, if you want to find the derivative of e phi with respect to time, name shows e phi does not depend on t, it depends on phi. Okay, so I'll use what I know. So I'll say the derivative of e phi par rapport au temps is going to be the derivative of e phi par rapport à phi, and then the derivative of phi par rapport au temps. Or the derivative of e phi par rapport à phi is moins euro, like so. And then the derivative of this phi that we have here is phi point par rapport au temps. It's going to be a dérivé temporel. So phi point and then euro. So these things you must know them by heart. So this is le vecteur vitesse en coordonnées cylindriques. Ok? Je passe? Wiza? Tassila, Natasha? Is it okay? Right, disconnection. Let me just reconnect one more time. Bien. You're not seeing the screen, right?
You're not seeing the screen.
Yes.
Okay, let me share the screen one more time. Right, so Are you able to see the screen now? Okay. Très bien. So are you able to follow? Up to this point, we've given the expression for le vecteur of vitesse en coordonnées cylindriques. So I will now move to le vecteur accélération en coordonnées cylindriques. C'est très très simple. Même chose, we're going to use this result that we have here. Now, of course, there's one quantity that I've forgotten to put here. It's plus z point EZ. Simple. Okay. So, so normalement, le vecteur accélération, we can use gamma to represent acceleration, is of the point M in the reference frame R is going to be equal to the derivative of the vector of vitesse in this reference frame R, and then par rapport au temps, and then now we found the vitesse. We found the vitesse. C'est simple. We found the vitesse. So we have rho point and then euro, like so. And then I'm just copying the expression. And then rho, and then phi point, and then e phi, and then z point, and then k, like so. Right, so we know that the differentiation operator is distributive, so I can distribute it over the sum that we have here. So here we have a product, so we apply the product rule. So if I apply the product rule, I'm going to get rho point point, like so. I'm going to get rho point point, then I'm going to leave euro alone, and then now I'll leave rho alone, and then I'll differentiate euro. Euro with respect to time is, remember, there's going to be that phi point and then e phi, like so. I've written it on the previous page, so we are done with this part. And then plus, here we have a product of 3 items, not 2, but how many items? 3 items. So we differentiate first of all rho and leave the others. So when we differentiate rho, we'll get rho point, and then we'll have phi point, and then e phi. We now differentiate the second one and leave the others alone. So we have rho, and then phi point point, like so. Okay, and then e phi, like so. And then now we differentiate the e phi and leave the other two alone. So we will have plus. So we'll have, there'll be a minus, sorry, because now I'll tell you why there's a minus here. Well, it's because there'll be a minus, so we'll have minus. Now we're leaving rho alone, and then phi point alone. Then the derivative of e phi par rapport au temps is going to give rise to a phi point. So here we'll have squared, but then remember that there's a negative. And then here we're going to have euro, like so. C'est simple. And then we are done. Now plus the derivative of z with respect to time is going to be z point point, and then ez, not k but ez. Remember I said you'll be seeing these things, but here I just want to be consistent. I'll use ez, and then ez, and then I have to now to leave z point alone and differentiate ez. If I differentiate ez, it's going to give me 0, because the ez in the cylindrical coordinate system is the ez in the Cartesian coordinate system, and it is called constant. Now let's factorize everything that has an euro. We put it. I mean, we group the terms. Let's group the terms following the unit vectors. So we're going to have rho point point minus rho phi squared, and then this is going to be euro, and then plus rho phi point, and then those will give me plus 2 rho phi, e phi, like so. This entire thing, and then finally plus z point ez. C'est clair? Do you have questions? Do you have questions? Weezer?
I don't have a question.
Très bien. Natasha? Tassila?
Wait.
Where?
The last expression here.
For the last expression, we've just grouped the terms. Grouped the like terms.
No, the two. This is two.
Yes, the
Two.
two
Fit.
phi, yes, 2 rho phi.
Okay.
Yeah. So if you just observe what is happening here, you'll be able to find the last expression. Allez, bon, this is at least we're done with the first part. So we've expressed le vector vitesse, vector accélération in the Cartesian coordinate system. Même chose, vector vitesse, vector accélération in the Cartesian coordinate system. So we've done all that good stuff. So next time we'll look at le mouvement relatif. We'll talk about things like le vitesse d'entraînement et le vitesse de Coriolis. And after that, we'll look at le changement de repère. And then finally, dynamique du point, matériel. And then we'll also be doing exercises as we proceed. So I already sent you the two exercises. So what we're going to do is that we'll see how best we'll sort of like this same week try to finish everything. Like we solve those exercises and we finish up. We look at the mouvement relatif, and then we can do the exercises. And then the other time next week maybe we can look at le changement de repère. Okay. So if you don't have any questions, we're going to call it a day. Otherwise, you can ask your questions. So maybe Tassila is this. Okay. So c'est bon? What?
No, I have a question.
Yes, what is your
I
question?
have a question.
Yes, what is your question?
This is not offending for acceleration. These are the expressions you follow like this.
Yes, these are the expressions, but you should not memorize them. You should understand how to find them.
Yes. Okay.
Yeah.
You said the example here represents vector vitesse, so
I don't think I got the last part. I didn't get the last part.
then you just identify for the experiment. Then you said that the gamma is just represents vector vitesse.
You know, gamma is accélération. C'est le vecteur accélération. C'est le vecteur accélération. Yeah. Okay. So we're going to end here for today, and then we'll continue. I'll tell you when. Okay, but it has to be a time this week so that we also solve those exercises. So we'll end here for today, and I'll see you guys next time. So you're free to leave the meeting.